Okay, so let's take a look at atomic radius. Atomic radius is exactly as you would imagine it. So if I have my nucleus and I have a bunch of different shells of electrons, the furthest electron out is going to be the distance between those two is going to be the atomic radius. So valence electron, this distance right here is going to be radius. We have a handful of different types of atomic radii or radii. You have an atomic radius, which is a neutral atom. And that's what we're going to look at here. But we're also going to look at ionic radii, which is from as you would imagine, a cation or anion. And cations and anions are going to affect it. But again, the idea is ionic or atomic radius. Atomic radius is a neutral atom. So we have increasing atomic radius. So going from left to right, okay, we have to think about what we know about Z effective, okay? What we know about Z effective is the fact that going from left to right, Z effective increases. So increase in Z effective, again, this is from left to right, equals a stronger pull on those valence electrons. The stronger pull on the valence electrons ultimately means a decrease in radius. Okay. The other value that affects atomic radius is by increasing the value of n. And we saw this when we were talking about principal quantum numbers. Principal quantum number, the increase in n equals an increase in energy equals an increase in size, right? It gets further and further and further away from the nucleus. So down a group, we see an increase in n equals an increase in radius. Across a period from left to right, we see an increase in Z effective, which equals an increase or decrease in radius. And in class, we are probably going to be covering, calculations of those Z effectives, okay? So how do we actually use atomic radii? Well, we use atomic radii by kind of looking at different shapes. So natural gas is odorless, so methyl mercaptan, CH3SH, is added to provide odor and a warning for potential glass leaks. What are the predicted bond length for SH, SC, and CH? So what we have is, let's draw the Lewis structure for this thing. So carbon with 3 hydrogens on it, a sulfur with 2 lone pairs, and a hydrogen off of it. And this is the Lewis structure that we have. From this, we can actually look at our SH. So let's take a look at what different radii that I have. So I am going to highlight these things. So let's take the carbon, which is typically black. Let's see what this looks like. So what we get from a carbon atom is this kind of nuclei. Let's draw it this way instead. So here's my carbon. Okay, there's my carbon atom. And of course, it has 3 hydrogens attached to it. 3 hydrogens attached to it. Let me just actually take this. So I've got 3 hydrogens. 1, 2, and I'll move that other one just a second. Use that later. There we go. So those are my 3 hydrogens attached to it. And then attached to that, I have a sulfur, which is a little bit bigger. And typically sulfur is red or yellow. So here's my sulfur. It's actually quite a bit bigger than, there we go. So I have a sulfur attached to this, attached to the carbon. And then I have this 1 hydrogen that's attached to that. Okay, so this is what it looks like just in terms of radii. And what we do know is the distances between these things. So if I actually take a look at this is the center of these, and I'm going to connect them together with center, 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 center. And we're going to connect these together with lines because these are the bonds that we're seeing. Okay, so again, the sulfur radii, let's go back and look at our sulfur radii. Sulfur has a radius of 105. And so first of all, 105, let's talk about this idea of radius in angstroms. Angstroms are kind of the old thing that they used to use. So I am going to actually convert this. So 1.05 angstroms is equal to, you're going to move the decimal twice, 105 picometers. We're going to use picometers. That's the standard that we use now. So we're going to call that 105 picometers in terms of the atomic radii of this. Okay. Okay, yeah, 105 picometers. So the distance between, this is 105 picometers. And this one is also, because if we're looking at here to here, this is also 105 picometers, okay? So we know that those distances. And then carbon, so let's take a look at carbon. Carbon we see is 0.76 or 76 picometers. So my carbon is 76 picometers. And so all of these are 76, 76, 76. Hydrogen is going to be tiny at 31. Okay, and in fact, I'm going to erase some of these. Sorry if you wrote them in. And there we go. What did I say it was? It was 31 picometers. So this is 31. This is 31. So on and so forth. So what is we're going to do these calculations. So if we're taking a look at the distance for the radius of an SH bond length equals the radius of hydrogen, which is right there, plus the radius of sulfur, which is right here. Okay, so I have 31 picometers plus the 105 picometers for a total of, what is that? 136 picometers. Okay, and so we do the rest of these calculations, right? So what is the length of a CH? What is the length of an SC? And we have all of the lengths that we're going to need. So the CH is going to be 76 plus 31 for a total of 107 picometers. The length of SC is 105 plus 76, which is going to be equal to 181 picometers. Okay, so we can calculate bond lengths for all of these. And I think that's all of our bond lengths. Yeah, that's all of our bond lengths that we need. So we have 181, 107, and 136. So from these, let's take a look at our predicted versus actual calculated and experimental from this thing for SH, CH, or I guess SH, SC, and CH. So the predicted for SH was 136. 181 for SC, and 107. And the experimentals were 133 for SH, 182 for SC, and 110 for the CH. So actually they're all pretty close to what we have. So the good news is if we're looking at a molecular compound like this, we can actually see that we have pretty close bond lengths in agreement with our spectroscopic data. So we actually look at these through spectroscopy. So these are actually pretty close all in all. Good. Okay, so that's the idea. Again, radius increases, but we can use these radii to actually look at structural shapes. So trends in trends in cationic ionic radii. So when we remove an electron, okay, so when we remove an electron to form a cation, and the sum is the cations will always have a smaller radii than the parent. So cations will always have a smaller radii than the parent. Well, why is that? Well, let's think about this in terms of, and the radius we should always be thinking about Z effective, Z minus S. By removing electrons, shielding constant, decrease in shielding by removing electrons. If we remove electrons, that means we're going to see a smaller shielding value equals an increase in Z effective. Because if it's the same element, Z shouldn't change. So by reducing S, Z effective increases, it's a smaller pull, a longer pull, a harder pull from the nucleus or larger pull from the nucleus. It's going to shrink it down. Okay, good. And as you could predict, anions are always going to be larger, always larger than the parent. All of these values, by the way, are in picometers. And again, the opposite is true for this. If you're adding electrons, you are increasing the shielding. By increasing the shielding, you're going to see the opposite effect where Z effective is actually going to be larger, or Z effective is going to be smaller. Good, makes sense? Fantastic. Let's see here. I do not remember why I added this in. Let's see here. Why is size? Yeah, why is size important? Size is important because in certain instances you need to have certain size ions fit in certain locations. So that's why it's important to understand why you have certain sizes in reference to others. So it's kind of the charge discharge of lithium. Lithium needs to be able to migrate across. All right, moving on to the ionization energy. I think I am probably going to do ionization energy in class along with electron affinity. Well, no, I guess I'll do it right now. Ionization energy. Okay, so ionization energy is the energy required to create an ion. It's important to understand ionization energy is, okay, let's see here. Ionization energy is, if I have, there's my nucleus, positively charged. I have an electron around the outside. I am going to put some amount of energy into this electron. And that electron is going to be ejected. We did this looking at spectroscopy, so energy is important here. Ultimately, the question is, how much energy to remove an electron? Right? So if I have some atom, I'm going to put some energy in, and what I'm going to form is the positive charge. So by how much energy do I have to put in to create a cation? That is ultimately what ionization energy is. How much energy to create an ion? And this is what we have. So what we notice is in terms of trend, okay, just in terms of trend on the periodic table, we notice that the noble gases have a very high ionization energy and the group ones have a very low ionization energy. So from left to right, we tend to see an increase across a period. Across a period, you tend to see an increase in ionization energy. But there are a couple of anomalies that you need to be aware of. We need to take a look. So here is my lithium to neon. What we notice is, and we're going to talk about these in class in more detail. So this is nitrogen. What is going on there, right? Why is nitrogen? And also, so why does nitrogen have a higher ionization energy than oxygen does, right? Why do we see gallium drop? Why do we see this climb for the thing before gallium, which is zinc? This is zinc, right? So we're going to talk about these in class. Yeah, we're going to talk about these in class because I think it's certainly worth looking at. So we will fill out kind of all of this stuff in class. In terms of ionization energy, first ionization energy is going to be X as a gas yields, and this is, I just did this above, X plus as a gas plus 1 electron. How much energy is needed to remove the second? X plus as a gas yields X2 plus as a gas plus 1 more electron. Okay, so the second ionization energy is what does it cost me to get rid of this second electron? So we add those totals, or we don't add those totals together. What are those energy costs? So here's a look at ionization energy just in terms of this is first, this is second, this is third, this is fourth, this is fifth, and so on and so forth. So first ionization energy, again, it's lower than everything else because as soon as you form a cation, it's harder and harder to get rid of those electrons. So there we go. Those are the first, second, third, fourth ionization energy. What we do notice is we see these pretty massive jumps from here to here. But that makes sense because once I remove the first electron from sodium, now I'm in a noble gas electron configuration. So getting rid of that electron from the noble gas makes it significantly harder. So that's why we see those massive jumps between the outer shell, the valence shell, and the inner shell. Trying to get rid of an electron forming sodium 2+ is really difficult to do because you're getting rid of that electron from the inner shell. So it costs a ton of energy. So what we see is across the period. So again, sodium all the way to argon. This is across a period, okay? Across a period, we're seeing an increase in ionization energy. And so across a period, we see ionization energy increasing. Because again, this is the Z-effective argument. Z-effective increases when we go from left to right, creating a stronger interaction. Right? How about down a group? Well, we don't actually have anything, so let me give them to you. So lithium had 520. Sodium has a value of 496. Potassium, rubidium, and cesium. Potassium is 419. Rubidium is 403. And cesium is 376. So as we go down a group, ionization energy decreases. Why is that? Electrons are higher energy and further from the nucleus. They're much easier. Their Z-effective is, although it remains the same, they're further and further away. So it actually is much easier to get rid of because their N is larger, right? Increase in N, it's further away from the nucleus. So increase in N is ultimately the reasoning behind that. All right, so write the equation for the second ionization energy of magnesium. Why is the third ionization energy of magnesium unlikely? What is more easily ionized, nitrogen or oxygen? Why or why not? So try those out. Write the electron configuration or the orbital diagram for nitrogen and oxygen. That might help us with the conversation above, which we're going to have in class. Next up, let's take a look at electron affinity. This is a little bit less, so this is the opposite. Again, electron affinity is chlorine or some element plus an electron making the -1. So we're creating an interaction. that means that all of these are going to be exothermic, unless otherwise stated. So all of these values are negative because we're creating an interaction between a nucleus and a negative charge. So that's why you see the negative values, except we don't see the negative values for beryllium. Nitrogen has a positive value. All of these have a positive value. So the question is, why do they all have a positive value for electron affinity, adding an electron, creating that negatively charged anion? Okay, so we'll talk about that in class as well. Again, down a group. So just to sum up, you can go back to that and take a look, but electron affinity down a group decreases, electron affinity increases across a group. When an electron is added to a nonmetal except group 8A, energy is released. Okay, so we'll talk about why those energies change in that way, but it has to do with electron configurations. Next up, electronegativity. This is similar to electron affinity, its ability to kind of pull in electrons. These values are, you don't need to know them, but it's important to know that fluorine has the highest value. So down a group, I don't think I have this, do I? Oh, I do have it. Down a group, electronegativity decreases, and across a period, electronegativity increases. And if we think about electronegativity, of course, it increases from left to right because fluorine likes to add electrons. Down a group, the opposite is true. We are going to be talking about something called delta En, or change in electronegativity, the difference in electronegativity. It's the difference in electronegativity across a bond. Okay, so it's going to tell us, it tells us about the interaction. It tells us about type and strength of that bond. Okay, so the delta En is actually pretty straightforward, the idea, the concept behind it. So if I have hydrogen bound with hydrogen, the electronegativity of these two things, hydrogen is equal to 2.1 in both cases. So the delta En of that bond is equal to 0, right? The difference of that is equal to 0. So the delta, we usually take the absolute value of it, but delta En is equal to 0, which is the change in electronegativity. This is going, what this will tell us in the future, and we're going to get here, you don't have to know this. This is a covalent bond. Turns out a covalent bond is going to be between 0 and 0.4. That's the, if there's a difference in electronegativity between that. Okay. Next up, if I had something like hydrogen and carbon, again, the difference is 2.1 and carbon is 2.5. Absolute value gives me a delta En of 0.4. This is on the upper end of being a covalent bond. But if we look at something like HF, okay, HF has a 2.1 for the hydrogen. It has a 4.0 for the fluorine. So the difference in electronegativity for this is going to be 1.9. That's a pretty massive number. And so there's a couple of things. So the way that we can think about this is the electrons are kind of preferring to be over near the fluorine. Okay, so what we would have is, if we were looking at this in terms of like electron density, you could imagine it like the electrons are kind of piling up over here, and there's just very few, there's a lot more electrons over in this region than near the hydrogen. With that, that does a couple of things. So first of all, it makes this side of it kind of this positively charged. Now it's important to know that we're going to use this little delta, meaning it gets a small positive charge over here by the hydrogen and a small negative. It's not a full charge, it's not an ion, because that would form an ion. So what this little delta means is it's a slightly positive charge. And this means it is slightly negative in charge, okay? The other way that we do it is we use this thing called a polar vector, where the electrons are kind of in this direction towards fluorine, right? So this is the positive end, this over here, that's what create that. It means that it's slightly positive. We call this thing a polar vector. It shows you the direction the electrons are pulling. All right, so ultimately what that means is this thing is going to kind of behave like a magnet, where this side is negatively charged, where the fluorine is negatively charged, and where the hydrogen is positively charged. And we're going to talk about what that means. In terms of bonds, the 1.9, what this is called a polar, because it has one positive, one negative side, polar covalent. And a polar covalent occurs between 0.4 and 1.9 differences. So it's really important to understand that's how we use electronegativity. Yeah, that's how we use electronegativity. Yeah, and I guess we'll just do one more. If I have sodium with fluorine, sodium is 0.9, fluorine is 4, so 4.0. The delta En for this is 3.1. Anything, basically anything greater than 0.4, I got that backwards. Anything greater than 0.4 or 1.9 is known as ionic. We form an ionic bond there. Okay, so we're going to use this much more, so we're going to talk about it much more, but the differences are going to be important, and that's electronegativity. Electronegativity kind of follows the same trend as electron affinity. Those two things kind of get conflated sometimes, but yeah, that's kind of what we're looking at for that. And I think that is all we're doing. Yeah, so we're going to cover electron affinity and ionization energy in class in detail. So we'll finish these notes in class. All right, perfect. I'm just trying to end this.